Welcome to EET1025C. This is Fundamentals of AC Circuits, and this is the first lecture in the course where we're going to do a review of some important topics from DC circuits. So the learning objective for this video is to review some important things you should have mastered in your DC circuits course. In order to be successful in this course, which is AC circuits, you really must have a very strong, firm foundation in the following. Applying Ohm's law, being able to identify a series relationship between two or more resistors, being able to determine the equivalent resistance of a series parallel circuit, being able to identify a parallel relationship between two or more resistors, being able to apply a current divider to determine an unknown current, and being able to apply a voltage divider to determine an unknown voltage. These are the most important tools that you should have covered in your DC circuits class. And because they are so important, I'm actually going to spend the first lecture just going over a quick review of these tools to make sure that you have a firm foundation, because we will be using these things throughout the semester very heavily. So first, to review Ohm's law. When we're analyzing an electric circuit, a simple and helpful tool is Ohm's law, which describes the relationship between voltage, current, and resistance. So we know that Ohm's law is voltage is equal to current times resistance, or V equals I times R. We can manipulate Ohm's law to solve this equation for current or resistance. And basically those three ways that we can use Ohm's law are shown at the bottom of the screen. If you have trouble remembering Ohm's law or how to manipulate it, this pyramid is a quick way to remember Ohm's law. Basically, if you cover up what you want to find, it gives you a shortcut to the equation for that particular value. So if you want to find voltage, it's I times R. If you want to find current, it's V over R. If you want to find resistance, it's V over I. So that's Ohm's law. We will be using Ohm's law very heavily throughout the course. It's very simple and straightforward. You just need to remember it. Now, it may seem very elementary that I'm going to review what a series circuit is and what a parallel circuit is. However, I've taught this course many times, and I can't tell you how many times throughout the course that a student will make a mistake as simple as not identifying whether two things are in series or in parallel. So I am going to review it one more time because it is very essential to understand these two relationships. So in order for two elements to be in series, they have to have the same current. And typically when we describe a series circuit, we say that a series circuit provides only one path for current between 2 points. And that's how the current is the same through each element in that circuit. And on the screen are some examples of elements that are in series. And as we go throughout the course, I'm going to constantly remind you not to rely on what the circuit looks like. The only definition you should be using to identify whether two things are in series is by following the flow of current. Does the same current flow through these elements? If they have to have the same current, they are in series. It does not matter how the circuit is drawn. The orientation of the resistors doesn't matter. What matters is the path. So you should get very used to actually following the path of current with your finger. So for example, in this first circuit, we can follow the path clearly from point A to point B. These are in series. We can follow these around. This is in series. Here's a great example of where some people may look at this and without thinking say that's a parallel circuit. Just because the resistors are drawn with a parallel formation doesn't mean they're parallel resistors in the context of electronics. Always remember to start from one point and trace the path of current. So in this third circuit here, if we trace the path of current, we can see that there's only one path, which means these have to be in series. So this is a great example of what I mean when I say don't rely on what the circuit looks like. Rely on the path of current that you can follow. If you look at picture D, again, we have one path. And then picture E, another example of how it might be easy to glance at this and without really thinking say, oh, those are in parallel. That's not true. There's only one path that we can follow. Therefore, these are in series. So as we go throughout the semester, you're going to have to calculate a total impedance based on whether two things are in series or in parallel. And you're going to have to rely on this definition and this definition only to determine that relationship. On the breadboard, here's an example of how you may wire resistors so that they can be in series. So the schematic is shown on the right. We've got 5 resistors and 1 path of current. And then this is how we might wire that on the breadboard. Remember that a column represents a connection, so any two things that are in the same column are connected. So we could have our voltage source connected to resistor 1 right here, and current would flow through that resistor, through this wire, through R2, through this wire, into R3, through this wire, into R4, through this wire, into R5, and then this is where we'd have our connection back to ground. So again, another example of just looking at this breadboard and how the resistors are laid out on the breadboard, it may not be obvious that they are all in series, especially with the resistor R3. You may look at that and say that's parallel, but is it really? If we follow the path of current, these are all series resistors. So once again, I'm going to remind you as we go throughout the course, don't look at how the picture is drawn, trace the current for yourself, and then decide based on the path of current whether your elements are in series or in parallel. A reminder of calculating total resistance for resistors in series, you're simply going to add them up. So your total resistance for resistors in series is just going to be a sum of each individual resistor value. When we look at current in a series circuit, we know that at any point in the circuit, the current is going to be the same. All the resistors in series must have the same current flowing through them. Again, it seems elementary, but as we go forward in the course, this elementary topic becomes a little bit harder to see when we have a more complex circuit. So just a reminder that when you have things that are in series, they should have the same current flowing through them. And now we have resistors in parallel. The definition that you should use for a parallel circuit is that it has to have more than one branch or more than one path for current to flow through. And eventually all of your different paths must meet again or rejoin at some point. That's our definition of a parallel circuit. Again, we're not going to look at how the circuit is drawn. We're going to trace the path of current, and we're going to ask ourselves, did the current split, take two or more paths, and then reconnect? If so, each resistance along each of those individual paths is in parallel. So if we look at circuit B, we have a voltage source. We can see that the total current will leave the voltage source and go this way. And at this point, the current will split. Some will go through R1, some will go through R2, and at node B, our two paths rejoin. That's our definition for parallel resistors. So these two resistors are in parallel because we have two paths for current to flow, where current has split and then rejoined. Image C is another example of a parallel circuit where we just have more resistors. So our total our total current flowing from the voltage source is going to come to node A, where it's going to split. Some will go through R1 and some will go this way. The amount of current flowing into this node will split. Some will go through R2 and some will go this way. The amount of current flowing into this node will split. Some will go through R3. The rest will go through R4. And this is our common point right here, where all the paths recombine. So these four resistors are in parallel. Here are some examples of parallel circuits. The way we're going to determine if resistors are in parallel is we're going to look at if there is more than one current path or more than one branch between two separate points. And the other thing about parallel circuits is that the voltage between those 2 points is the same across all the branches. Remember, resistors in parallel have the same voltage drop across them. And here are 5 examples of resistors that are in parallel. We're not going to go based off of what the picture looks like. We're only going to trace the path of current. So if you look at image A, current comes from point A. This is where your voltage source would be. It splits. Here's path 1. Here's path 2. Here's where they rejoin. These two are in parallel. If you look at image B, we can clearly see that the current will flow from point A here. It'll split, take two paths, recombine, and then exit. So that's a parallel circuit. Same thing with image C. We can see that there are two paths where current splits and then rejoins. Image D, as well, we have two paths where current splits and rejoins. Now, I would say for the most part, these first four images are pretty intuitive. It's not very hard to tell that these are in parallel. But look at image E. Just by looking at it, it doesn't necessarily seem like these are in series or in parallel. So let's trace the path of current. Current will start to flow from point A, come to this node, and the current will split. Some will go this way. Some will go this way, and it reconnects right here. That's our definition of a parallel circuit. So this circuit is also an example of a parallel circuit with two resistors. There are two paths. So again, as we go throughout the course, you're going to have to rely on the path of current and the path of current only to determine if two or more elements are in parallel or if they're in series. So remember again that resistors in parallel have the same voltage across each of them. This may or may not be equal to the source voltage. That depends on how the circuit is wired. So three things can be in parallel with each other, but not in parallel with the voltage source. Or you could have three resistors that are all in parallel with each other and the voltage source. So don't assume that just because you have three resistors in parallel, that their voltage is always going to be equal to the source. The examples you see on the screen show that to be true. We have three resistors, they're all in parallel with each other, and they are in parallel with the source. So these three resistors would all have the same voltage as the source. But we can't assume that every time we see two or three things in parallel. As an example, I'll just draw a really quick circuit on the screen. If I had a resistor that was like this, and another one that was like this, and another one that was like this, these two are in parallel with each other, but they are not in parallel with the voltage source. There's another resistor up here, which means there has to be a voltage drop across that resistor, which means these two resistors, while they do have the same voltage drop, they have an equal voltage drop. That voltage drop can't be equal to the source. So that's what I mean when I say we know that resistors that are in parallel have to have the same voltage across them, but that doesn't necessarily mean that we know automatically the value of that voltage drop has to be the source. We have to look at the orientation of the circuit and decide that. All right, so moving on to current dividers. We are going to use current dividers and voltage dividers very often. And I can't stress how important it is to truly understand how to set up a current divider and a voltage divider when you're doing your calculations. As we go throughout the semester, we're going to be looking at some circuits that are a little bit more complex than the ones you looked at in DC circuits. So it may become very easy to mess up what seems like a simple tool, a current divider. And you really have to understand how the current divider is supposed to be set up. So we're going to review that. So in a parallel circuit, the total current into a junction or a node of parallel branches will divide among the branches. For this reason, we can call a parallel circuit a current divider. It will divide the current into two or more paths. So here's an example. We have a voltage source. You have your total current flowing into this node, and the current splits. And a current divider is a quick tool we can use to figure out how much current went through R1 and how much current went through R2. So this is our formula for a current divider. This is the same formula that you have seen in DC circuits. So basically we can say that the current through a particular branch, we'll just call that branch X, is equal to the total resistance divided by the resistance of the branch multiplied by the total current going into the junction of parallel branches. So let's break that down. First of all, when we use a current divider, RT is not the total resistance of your entire circuit. One of the main mistakes I see when a student sets up a current divider is that they put RT as the total resistance of the entire circuit. That's not always true. So if I go back to the first circuit, for example, I only have 2 resistors in this circuit. So my total resistance is going to be this parallel combination. But what if I had a circuit that looked like this? Just as an example, the total current is going to flow through that resistor and then split into 2. The RT that you see in the current divider equation is simply the parallel combination of all of the paths after the split, not the total resistance in the circuit. So when you look at this equation right here, RT is going to be your parallel combined resistance, so your parallel combination of all the paths in question. So if the current splits 3 ways, you're going to find the total resistance of those 3 paths. If the current splits 2 ways, you're going to find the total resistance of those 2 paths, not the total resistance in your circuit. Okay, the caveat to that is if your circuit only has the 2 parallel paths. But in general, you're going to think of this as the total resistance of all of my parallel paths combined. That's your numerator. The denominator of your current divider is the resistance of the path in question. Keep in mind, if you have 2 resistors on the same path, you would have to combine those resistance values and put that in as your denominator. So you have to look out for how much total resistance is along the path you want the current for. And then we're going to multiply by IT, but IT here is not necessarily the total current in your circuit, it's the total current that is being split among your paths. So you may find that you have a circuit where there's a particular node, the current is going to split at that node, but the current going into that node is not equal to the total current in the circuit. Those are 2 different values. So when we set up our current divider, we have to remember, what does RT really mean? What does RX really mean? What does IT really mean? And so I'm going to do some examples to help you reinforce the idea of a current divider. Voltage dividers are another tool we will use. Remember that the total voltage drop around a single closed path divides among resistors that are in series. And that voltage will divide proportionally to the values of your resistors in your series path. So that's what we call a voltage divider. So when I have a group of resistors that are in series, I can set up a voltage divider to quickly figure out the voltage drop among a particular resistor or a particular group of resistors within that series. Here's our equation for a voltage divider. We say that the voltage for a particular resistor, the voltage for a resistor X, is equal to resistor X, that resistor value, divided by the total resistance. Now this total resistance, again, is not necessarily the total resistance in your circuit. It's the total resistance of your series path. If I'm setting up a voltage divider for just these 2 resistors that are in series, my total resistance is the total resistance of that series path. This circuit may have other elements going on to it. This may be just a snippet of a much larger circuit. But if I know the voltage from this point to ground, I can set up a voltage divider to figure out the voltage for R1 or the voltage for R2 by following this formula. So that's how we set up a voltage divider. The other tools that you should have learned in your DC circuits class are basically how to solve a series parallel circuit. How do you use Ohm's law, Kirchhoff's laws, voltage dividers, current dividers? How do you figure out when resistors are in series? How do you figure out when resistors are in parallel in order to basically find the current and the voltage drop for each resistor in the circuit? So on the right is an example of a series parallel circuit. This is an example of something that you should have learned how to analyze in your DC circuits class. just looking at it based off of how it's wired, you should be able to figure out what's in series and what's in parallel. For example, look at R4 and R5. Are they in series or are they in parallel? Remember, don't look at how it's drawn. Ask yourself about the flow of current. If current's going to start from the voltage source and flow this way, it's going to split here and here, and then recombine at this node. That means R2 and R3 have to be in parallel. The current is going to recombine at this node and then split again, where some will go this way and some will go this way. And then the current will recombine right here. So we have two paths. Therefore, R4 and R5 are also in parallel. So these are the type of relationships that you should have mastered in your DC circuits class. I'm hoping that as you're looking at this circuit on the screen, that you can confidently say, oh yeah, I know how to find the total resistance for that circuit. I know how to find the total current for that circuit. I know how to find the current for each branch of the circuit. I know how to find the voltage drop for each resistor. That is my hope. And if you have not gotten to that level of confidence yet, now's your time to review. Now's your time to go back over it, to brush up on things you may have forgotten or things that you didn't really understand the first time around, so that as we go forward, you can go forward on a strong foundation, because these are the things you will need to be successful in this class. So now let's do some examples. We're going to use voltage dividers, current dividers, etc. to analyze a few series parallel circuits. So take a look at the circuit on the screen, and here are the things we're going to find. We're going to determine the equivalent resistance or the total resistance of the circuit, the voltage across each resistor, the current through each resistor, and the value of the source voltage Vs. So we don't know how much voltage is applied. We do know the total current. We have 5 resistors, and we're going to analyze this circuit using Ohm's law, voltage dividers, and current dividers. Let's start with the equivalent resistance. So let's look at the relationships. We see that the total current is going to come into this node and split. And then it's going to recombine right here. Therefore, R1 and R2 must be in parallel. We see that the current is going to then enter this node here and split. And we have 2 paths. So this path is in parallel with this path. But we have to remember that's the entire path. So first, we'd have to combine R4 and R5 because they're in series. They have to get the same amount of current because the current flowing through this path is going to flow into R4 and out of R4, then into R5 and out of R5. So these have to be in series. So first, we're going to combine R4 and R5 in series. Then that combination is in parallel with R3. We're going to combine that together. We're also going to combine R1 and R2 to make that a combination. And then this group combined is in series with this group combined. So I'm going to start with R1 and R2. They are in parallel. I'm going to call that Rx. Every time I make a combination, I'm going to give it a new name. So R1 in parallel with R2, I'm just going to call that Rx. There's your calculation for parallel resistances. Again, you should have learned that calculation from DC circuits. And these two combined, we get a total of 687.5 ohms. Next, I'm going to combine these 2 branches. I'm going to combine R3 with this R4, R5 branch. I'm going to call that combination RY, just giving it a new name. You can call it RA, RB, R1, R2, whatever you want to name it is fine. It's just giving it a new name so that I can always reference back to that specific combination later. So I can see that RY is going to be the parallel combination of my 3.9K and my R5 and R4 combined. I'm going to add these up, and then I'm going to combine that in parallel with R3. So I get that this entire section right here is equivalent to 1.35 kilo ohms. So at this point, I now have a circuit where we have Rx is in series with Ry. So now I'm going to add Rx and Ry together to get a total. There's my total resistance for this circuit, 2.0375 kilo ohms. Now I'm going to determine the voltage across each resistor and the current through each resistor. Okay, so I'm going to start by performing a current divider on R1 and R2. So here's a great example of what I was trying to demonstrate earlier. When we set up our current divider, we're going to take Rx, and Rx is the combination of R1 and R2. This is the combination we're going to be using for our current divider. We're not going to be using the total resistance of the circuit. We're only going to be using the total resistance of the two paths in question. So when I set up my current divider, I have to use Rx because Rx is my equivalent resistance for just these two paths. So remember, our equation for a current divider is Rx, our total resistance for both paths. Not the total resistance in the circuit, just the total resistance for these two paths. That's our numerator. Our denominator of the current divider is the resistance for the path we want the current for. I want the current for R1, so my denominator is going to be the value of R1. We're going to multiply this fraction by the total current going into this node right here before the split. In this case, the total current going into that node is the total current in the circuit. So we're going to multiply by 1 milliamp. And now we have the current through R1, 0.688 milliamps. From here, you can always use KCL to figure out the current through R2, or you can set up another current divider. Here's what your current divider would look like for R2. We're still going to have the same numerator because the current is dividing between R1 and R2. So I have to have the parallel combination of these two paths. That equivalent resistance is still going to be my numerator, but now my denominator is going to change, and I'm going to put R2 on the bottom instead of R1. That will give me the current flowing through R2. So this is how we set up a current divider to figure out the current through R1 and R2. Now we're going to use the currents we just found to figure out the voltages for R1 and R2. So we know the current, this is from the previous slide, and now we're just going to use Ohm's law to figure out the voltage drop for R1 and R2. Notice that you get the exact same answer. We should get the same answer. These are in parallel. Parallel resistors must have the same voltage drop. So here's a great example of where knowing that relationship helps you to check your work. When you understand the relationships, you usually have more than one way to solve a problem, which means you can guarantee that your work is correct most of the time. So since R1 and R2 are in parallel, we should have the exact same voltage drop for each if we use Ohm's law, and we see that that case is true. Next, we're going to perform a current divider on R3 and the R4 plus R5 branch. So notice that these two resistors form a branch. They are in series. So we're really going to combine those resistance values together as we look at that particular branch. So in order to find the current through R3, I'm going to set up my current divider. And for this current divider, I'm going to be using the combination of this branch and this branch, which is RY. We've already figured out that combination. So that combination is going to be the numerator of the current divider. So remember, when you set up a current divider, your numerator should be the combination of all paths that the current takes when it splits. In this case, that combination is the two paths, one through R3, the other path that goes through R4 and R5. So that combination, which is RY, is going to be the numerator of my current divider. The denominator of my current divider is going to be the path I want the current for. In this case, I want the current for R3. So that is going to be in the denominator of my current divider, and then I'm going to multiply by the total current going into the node before the split. In this case, I can see that the total current splits and goes through R1 and R2, recombines right back here, so this is the total current once again, and that total current is what's going into this node. So I'm going to multiply by the total current going into the node. In this case, that's the total current in the circuit. Remember that we can always assume that the current we're going to be multiplying by in our current divider is always going to be the total current in the circuit. It happens to be the case with this particular circuit, but that won't always be true. So when you set up your current divider, remember that you're setting up a fraction where the numerator is your parallel combination of all your paths. The denominator is the resistance of the path you want the current for, and you're multiplying by the total current going into the node before the split of your paths. So as we set this up, you can see that the current through R3 comes out to be approximately 0.346 milliamps. Now you can always use KCL to find the current that goes through the second branch, or you can set up another current divider. So in this case, we can see that the current through R4 and the current through R5 have to be the same current because they're in series. So when I set up my current divider for this branch, I'm going to use the same numerator because I have the same two branches that I'm looking at. So the numerator will be the same, the parallel combination of this branch and that branch, which is RY. The denominator is a great example of where you're not going to be looking at just one resistor when you set up a current divider. You're looking at the resistance of the entire path. There are two resistors on this path. They must be combined when you set up your current divider, and they must be combined and put into your denominator. So when I want the current through R4, I can't just do RY divided by R4 or RY divided by R5. I have to do RY divided by the total resistance of the path in question. This is one path, and these two resistances are in series, so we're going to combine them. So that's why our current divider has R4 plus R5 on the bottom. Again, we're multiplying by the total current going into the node, which is 1 milliamp, and now we have our current for R4 and R5. Next, we're going to use the currents we just found for R3, R4, and R5 to find the voltage drops for R3, R4, and R5, and each one of those will be found just using Ohm's law. So there's the currents that we found on the previous slide, and plugging into Ohm's law, we can get our voltage drops. Keep in mind that R3 is in parallel with the combination R4 plus R5, so these two voltages combined should be approximately equal to the voltage drop for R3. And if you add these up, you'll see that to be true. Next, we're going to determine the value of the source voltage Vs. That's not a value that was given in this particular problem, and we're going to calculate it. So one way to do that is to use KVL. That's not the only way. Oftentimes there are more than one set of tools that you can use to solve a problem. I chose KVL, but it doesn't have to be KVL. But here's a quick review of KVL. The sum of the voltage drops around a closed loop has to be equal to 0. So this is a closed loop. Basically the source voltage, R2 and R3 make a closed loop. If I add up these voltages, remember to consider polarity, I can say that the sum of R2 plus R3 plus the source voltage has to equal 0. And again, you have to consider polarity. So when I set this up, I have a positive voltage drop across R2. Remember that the polarity is derived from where the current enters versus where the current exits. The current enters R2 on the left side and exits on the right. Therefore, the positive terminal is on the left side where it enters, and the negative terminal is on the right. So as I go around my loop, I have a positive 0.688 volts. I have a positive 1.35 volts, and then I have a negative Vs. That's going to be my algebraic sum. And then I can move Vs over to the other side and solve, which I get 2.038 volts for the source. You could have also used the total resistance and the total current and Ohm's law in order to find Vs. So that wraps up the first problem. We're going to move on to another problem. This is a ladder network, and we're going to do the same exact thing. Find the voltage drop for each resistor and the current through each resistor. And with a ladder network, you have no choice but to use all of the tools at your disposal. You've got to use a current divider, you've got to use KVL, you've got to use KCL at some point. So we're going to analyze this ladder network and just practice using those tools one more time. So with a ladder network, typically you start from the end or the right in this case and work your way to the left. we can see that R5 and R6 are in series. They have to have the same amount of current flowing through them. There's nowhere else for that current to go, so we're going to combine them together. And our goal here is to combine all these resistors so that we can find a total resistance for the entire circuit and then find a total current. So I'm going to combine R5 and R6. When I make that combination, I'm going to call that RW, just giving it a new name so I can refer back to that value whenever I need to as RW. So I've made that combination, and now here's what my circuit looks like. Next, you need to identify the relationship between RW and R4. They are in parallel. The current that goes into node B will split. Some will go through R4, some will go through RW. They're in parallel. If you haven't seen this before, the double slashes is shorthand for parallel. You'll see me use that a lot during the course. So for step 2, we can say that R4 is in parallel with RW. We'll make that combination and we'll give it a new name. I'm going to call it RX. So Rx is the parallel combination of R4 and RW. Here is what the circuit looks like after we make that combination. Next, identify the relationship between Rx and R3. These are in series. All of the current that goes through R3 is going to flow through Rx. There's nothing else. All the circuit has been combined and collapsed up to this point. So R3 and Rx are in series, and we'll add those two values together and call it Ry. And here's what my circuit looks like after I have combined those two together. So now my relationship between Ry and the next resistor in line, which is R2, is going to be that they are in parallel. Current will split, some will go through R2, and the rest will go through Ry. So I'm going to combine R2 and Ry in parallel. Next, I have RZ. So that's all of my combinations up to this point, RZ. And I have one final resistor, R1. We can see that R1 has to be in series with RZ. Everything else has been combined, so there's nowhere else for that current to flow except through RZ. So I'm going to add R1 and RZ together to get a total resistance of 5.09 kilo ohms. That's my total equivalent resistance for the entire circuit. Now I can use that value to find the total current in the circuit. We also know that the total current in the circuit must be the current flowing through R1. So take our voltage, divide by total resistance, that's using Ohm's law. We have the total current as well as the current through R1, and that comes out to be 8.84 milliamps. So I know the current through R1, which means I can use Ohm's law and find the voltage through R1. And I have my voltage right here at the top. Here's my voltage, and I have my current written right down here. Notice I'm labeling each voltage with correct polarity. The positive is where current enters, the minus is where current exits. Now we're going to slowly work back the other way using what we know. Right now we know the current that goes into node A, and we know it splits. Some current goes through R2, some current goes through Ry. So now I'm working backwards. So let's set up a, you could set up a current divider to find the current through R2. We're going to set up KVL to find the voltage across R2. So the voltage across R2, if we were to set up KVL to solve for this, we'd have 8.84 volts plus whatever this voltage is, minus 45 equals 0. And if you rearrange that, you can get that the voltage across R2 has got to be the difference between the 45 volts you started out with and the 8.84 voltage drop across R1. So now we have the voltage across R2. And you can now find the current through R2 using Ohm's law. Take that voltage, divide by the resistance of R2. Now you have the current through R2. Remember, the goal is to slowly work our way back out until we know the current and the voltage for every single resistor. So now that we know the voltage for R2, this unlocks some new information. R2 is in parallel with Ry. We now know the voltage across Ry. That's one thing we can use. Or we know the current going into node A. We know the current going through R2. So we can use KCL to find the current that has to be flowing back through RY. Either one of those tools is something you can use to move forward. I chose to use KCL to find the current going through RY. So we know that 8.84 milliamps goes into node A, 4.41 goes through R2, so 4.43 must be left over to go through RY. Now remember, RY was the combination of RX and R3. So if I reverse that combination, I get this. RY was the combination of R3 and RX. We just figured out that the current going through RY is 4.43 milliamps. That means the current going through whatever RY replaced is also 4.43 milliamps. So we know that the current going this way has to be 4.43. So I know the current through R3 and the current through RX are 4.43. So since I know the current for R3, I can use Ohm's law and find the voltage for R3. Get 14.62 volts. So I'm slowly working my way through this ladder network, finding the current and the voltage for each resistor. Now, at this point, I know the current that's going through RX. I also know that this is a closed loop, and I know 2 of my 3 voltages around that closed loop. So I could use KVL to find the voltage across RX, or I could use the fact that I know the current going through RX to make my next step forward. I decided I'm going to find the voltage across RX, and I'm going to do that using Ohm's law. The voltage across Rx is going to be the current going through Rx, which we know is the current going through R3, which is 4.43 milliamps, multiplied by the value of Rx, which has previously been calculated to be 4.85 kiloohms. So I know the voltage across Rx. Now, keep in mind that if I know the voltage across Rx, I know the voltage across what Rx replaced. Here's what Rx replaced. Rx replaced R4 and RW. So the voltage across Rx is the voltage across R4. And I can use that now to find the current through R4 using Ohm's law. So I take the voltage that I just calculated, divide by the value of R4, I now have the current going through that branch. So I get 2.15 milliamps. At this point, I'm almost done. I'm down to the last 2 resistors. So remember now, R4 and RW are in parallel. You know the value of the voltage drop across R4, which means you know the voltage drop across RW. Or you know the current going into node B, you know the current going through R4, which means you can find the amount of current that was left over. Either one of these options are what you can use to continue forward. So I'm going to find the current through RW. I'm going to use KCL to do that. So I know that 4.43 milliamps goes into node B, 2.15 goes this way, which means 2.28 has to be what's left. I know now the current through RW. That means I also know the current through what RW replaced. What did RW replace? R5 and R6. So by finding the current through RW, I found the current through R5, as well as the current through R6, and that's going to be 2.28 milliamps. And now I can finish the problem by finding the voltage drop for each one of those resistors, using Ohm's law. Now I just so happen to get the same voltage because those resistors are the same value. So that's coincidence. You won't always see that depending on your resistor values. But now I have the voltage drops and the current through each resistor in this ladder network. The next thing we're going to do is look at the voltage at each node with respect to ground. Remember, when we measure a voltage with respect to ground, we're literally thinking about connecting a DMM. You have your 2 alligator clips. One clip will go directly at this point. The other clip will go directly to ground. So the voltage at point A is going to be the voltage from this point to ground, which is 36.16 volts. The voltage at point B would be the voltage from here to ground, which is 21.49 volts. And the voltage at point C would be the voltage from here to ground, which is 10.72 volts. So we've used a number of the tools that you've learned in DC circuits to analyze a ladder network by first collapsing all of the resistors until you have a total resistance, using that to find the total current, and then using a combination of KVL, KCL, Ohm's law, in order to find your other resistor values. This isn't the only way to solve the circuit. You could also have implemented some current dividers to find the current leaving some of the nodes if you so choose. So the idea behind the tools is to use whatever works. You can use more than one tool to find the same value. So at the end of the day, as long as your tool is the right tool for the job, you can use that tool. All right, so this is the end of my review. Again, I'm not going to reteach the entire DC circuits course to you. If you do feel like you need more review on the topics I have mentioned, please go to my YouTube channel, and it's under my name, Ashley Evans, and find my Fundamentals of DC Circuits playlist. That playlist has every video that I use when I teach that course. And if you still need to review KVL, KCL, Ohm's law, voltage divider, current divider, series parallel circuits, anything like that, you can go to my playlist and rewatch those videos from DC circuits. So again, this is supposed to be a review, this is supposed to be a refresher, and this is supposed to be a big heads up that as we go through the course, these are the tools you must have mastered in order to do well. The mathematics in this course is a little bit more complex than in DC circuits, so you're going to have a firm foundation of those tools as we add to it more complex mathematics. So, if you have questions about reviewing during this first week of the course, please send me a Canvas message or an email. I'd be happy to help you out and answer any questions that I can. And that is the end of this video.